Okay, I think it's now time to start. I would like to welcome you all to seminar
Recording
C,
in progress.
and the seminar on the physics of cold trapped atoms. And I am very happy and very grateful that you all sent the abstract and are participating in this seminar. So that's keeping alive the laser physics series of seminars, and probably or hopefully we will be able to meet again presentially next year in a first presential meeting after a long time. We have a very nice list of contributions to the seminar, and I divided in by three talks each section. So we don't get tired of staying in the computer all the time, and some of us wants to see the plenary talks. So we starting now a first section, and then we're going to go back. We end by 8:30. By 1:30 the UTC time, and then we restart at 4 p.m. UTC time and end by 5 p.m. UTC time. So every day we have two sections, and I was compressing everything in 2 days, but then more and more abstract came, so we're gonna have to advance or to the third day. So our seminar will be today, tomorrow, 4th of July, and one section or 1.5 section more or less in the 5th of July. I hope you all received the program, and the program is also in the homepage of the Laser Physics Workshop, and you can always follow this and everything. So this morning, we have three very interesting, or morning for me is like afternoon for many people. We're going to start, we have three contributions, and we're going to start with Yukalov. We all know Yukalov from the Bogolyubov Institute, a very important person in this, and with important contributions in the field of cold atoms and many-body physics. And today, Slava who is going to talk to us about nonlinear coherent modes and atom optics. So Slava, you have 30 minutes total. I hope you expend about 25 in your talk and leave about 5 minutes for open section or open questions and maybe some discussion. I will give you a warning when it's missing 5 minutes to end the 25 minutes, okay?
Okay.
So Slava, please, thank you for being with us, and it will be a pleasure to see your new report on the nonlinear coherent modes and atom optics. Please go ahead.
Okay. First of all, thank you very much, Wanderlei. I'm very glad that and grateful to you that you invited me. I'm going to talk about nonlinear coherent modes and atom optics, about some similarities between them. Of course, I cannot talk about everything in the world because there are many interesting stuff here, and I will concentrate on the topics of interest for the authors of the presentation and on some results obtained by these authors. So this is a kind of a survey. Therefore, I will not go into much details for each particular point, but will rather give the main ideas. And if there are any questions, then I can go into details. So how it is? I don't see. Page down. No, it doesn't work. Well, Doesn't work page down.
Okay, click on the presentation and probably we will start to go down. Just click on the presentation.
Okay.
Now try. Okay.
Okay, sorry. Excuse me. Okay. So coherent modes are the modes, the special states of Bose-Einstein condensate. The standard Bose condensate corresponds to the many particles that are piled down to the ground state. So the first questions which we are interested in, is it possible to create a kind of non-ground state condensate? Of course, if we are dealing with an equilibrium system and with an uniform system, this is not possible. But we are talking about trapped atoms where there are discrete energy levels. So in the equilibrium, if the system is both condensed, then the atoms pile down to the ground state level. And if we would like to create an excited state, that would be a Bose condensate, but not on the ground state level. We should, of course, apply some external fields. If we are able to transfer atoms from the ground state level to the excited level or the trap, then this would be exactly a non-ground state Bose condensate. This implies that we need to use some external field, for example, like this field, alternating field, which varies with the frequency in resonance with the transition frequency. And here immediately we see the analogy between this case and optics. In optics, we transfer by an external field electron to an excited level and then consider the radiation. In our case, dealing with Bose condensate, we transfer a condensate consisting of many atoms into a non-ground state level. So if we are able to do this, this will be exactly the non-ground state Bose-Einstein condensate. This is possible to do in different ways, applying one or more external fields. For example, if we are applying several fields, we can excite several modes in this way. For example, 3 modes can be excited by the cascade generation, which again similar to what happens in usual case of optics, or can be lambda type generation or V type generation. Coherent modes physically correspond to different shapes of density inside atomic trap. They are also called because of these topological modes, because their densities have different number of zeros, ground state or excited state, and like that. Mathematically, coherent modes are defined as the solutions of stationary nonlinear Schrödinger equation. In the case of trapped atoms, this is usually the case with the local interaction potential. And as soon as there is, in addition, an external field, then defined modes are connected through this time-dependent equation, where there is this external field that can excite one or several generated modes. In generating these modes, we have 2 main quantities. These are transition amplitudes. One transition amplitude is due to the interaction between atoms, and another transition amplitude is caused by the applied field. When dealing with resonance generation, we need to apply not very large fields. So these transition amplitudes are small as compared to the transition frequency. The solution to the time-dependent equation can be found by expanding the wave function into these coherent modes, like is written here, and this expansion with the coefficient Cn defines the fractional mode population. So these are the equations which we obtained from the nonlinear Schrödinger equation by substituting this expansion over modes. In the case of two modes, one ground state, another is generated excited mode. This is the equations that are obtained if we apply two external fields and deal with three modes. These right-hand sides depend on the kind of transition we are using, whether it is cascade, lambda type, or V-type transition. Another way is to modulate not the external potential or the trapping potential, which is the same, but the interaction between atoms. This is possible to do using the Feshbach resonance and modulating the magnetic field, like here. The result is similar. As soon as these coherent modes, so they have different shapes, then between them there occurs the phenomena that are typical for the interference of coherent objects, like the appearance on the interference patterns, Rabi oscillations, and internal Josephson current, because these modes have different shapes, different densities distribution inside the trap, and between different density distributions, there appear internal Josephson current. It is possible to study Ramsey fringes if there are two pulses by two pulses separated by some interval of time. Then it's possible to calculate the fractional population of the generated excited state. It has this form similar to the case of usual optics, but with the difference of that here the tuning includes not only the tuning from the resonance simply, but also these terms caused by interactions. This is interaction amplitude. And these are fractional mode populations on the excited level and ground state level. So actually delta is a function of time also. Similarly, the Rabi frequency, which is expressed through this effective detuning, also is a function of time. So a slightly more complicated formula, although it looks exactly as in optics. Then there is, when exciting, the effect of mode locking. This implies the following. When we start applying an external field with very small amplitude, then fractional mode populations never cross the line 1/2. There are oscillations of these populations around their initial conditions. If we increase the pumping amplitude, then we go from mode locked regime to mode unlocked regime, and fractional mode populations vary in the whole interval between 0 and 1. This transition between mode locked regime and mode unlocked regime happens on the line which is called in dynamical theory separatrix. It is written here. And the transition through this separatrix is connected with very sharp changes in the dynamics of the system. This is a typical phase portrait of population difference and phase, which shows the existence of mode unlocked trajectories and mode locked trajectories. So this is what happens when we cross this separatrix. Just before the separatrix, for example, fixing the amplitude of the pumping field in dimensional units, and looking what is the dependence on the detuning. At zero detuning, we have this picture. This is the excited. This is ground mode populations. Not touching the pumping amplitude, but varying just a little the tuning in the fourth digit, we have a jump when there appears this plateau and the period of oscillation doubles. Then changing the seventh digit, the tuning, again leaving the same pump amplitude, we go from the regime of mode locked motion to mode unlocked regime, where the fractional mode populations vary in the whole interval, like here. The transition through the separatrix is similar to the transition through the critical line in the theory of phase transitions. If we average over time our system and obtain an effective energy, then it is possible to look how specific quantities change when we cross on the separatrix line. It is possible to define the other parameter, which is the population difference, average population difference, pumping capacity, which is the quantity describing how the energy, effective energy, depends on the pumping amplitude, and it's possible to define a susceptibility, which describes the action of detuning on the other parameter. Calculating these quantities, we see that they behave as typical quantities close to a phase transition, where the pumping capacity diverges and susceptibility also diverges with specific critical exponents. There is a series of other effects that are similar to what happens in optics. It is possible to apply one driving field and create harmonic generation when we have not the correspondence of the pumping frequency with the transition frequency, but a kind of what in optics would be called two-photon transition, or several photon transitions. So it is kind of harmonic generation. It is also possible to generate the modes by parametric conversion, which reminds us of some kind of Raman transitions in optics. In general, this is sufficient condition to generate the excited modes. It is possible to consider atomic squeezing. If we define pseudo-spin operators, we have the same properties as standard spin operators, but which are composed on the creation and annihilation operators of atoms. Then, using these pseudo-spin operators, it is possible to define the squeezing factor in this way, and to consider the squeezing of the population difference with respect to population transitions. It turns out that for the case of generating several modes, we have always atomic squeezing because the squeezing factor is less than 1. Physically, this means that population fluctuations are smaller than phase fluctuations or current fluctuations. And from the experimental point of view, it implies that it is easier to measure atomic populations than the current. Similarly, in several mode generations, it's possible to define again the squeezing factor by defining effective quasi-spin operators. This is a calculated squeezing factor for the case of two modes. It is seen that it is always less than 1 and oscillates. This situation depends on the parameters on the system, but this is a general qualitative picture. Next, in other similarities, when we have several atoms, we can create the so-called entangled state, like Einstein, Podolsky, Rosen state, or Bell states, when we have a couple of atoms with two levels. Similarly, if we have many atoms and there are several modes, then we can create multi-cat states or multi-mode states. In our case, we are dealing with different pieces of Bose condensate, so it is possible in that sense to create a kind of entangled microscopic objects. Just schematically here, two condensate clouds composed of many atoms can be entangled in that way. In mathematical presentation, this implies the following. Since Bose-Einstein condensate is a coherent state, it is possible to define coherent states in the Fock space and consider, for example, the so-called coupled set of traps. Or another way, it is a kind of optical lattice. If this lattice is sufficiently deep, there are many particles here, and it is possible again to transfer simultaneously in several traps atoms creating the same modes. This is possible, for example, just shaking the optical lattice. By doing this, we can define the statistical operator of the system, which has the form of an entangled state, as seen here. Also, since experimental observable quantities are calculated as the averages using this statistical operator, then during these calculations, statistical operator acts on the functions of the given Hilbert space, and it produces new entanglement. The produced entanglement can be measured by defining the entanglement production measure written here and calculate for the case of an optical lattice composed of NL different deep sides. This is the entanglement production for the optical lattice of many traps, which is expressed through the entanglement production between the couple of traps. This is calculated entanglement production in the regime of mode locking motion. It oscillates very close to the initial conditions. And this is the oscillations of the entanglement production in the case of a mode unlocked regime. It is important that in principle we can vary and generate different behaviors of the entanglement production, since we can apply the external field, switch it on or switch it off. By doing these manipulations, we can create entanglement production in different shapes, like here, or in different non-equal time intervals, like here. So we can create different regimes of entanglement production. It is also possible to generate the coherent modes, not necessarily by a resonant field, but it is sufficient to use some field which is sufficiently strong, then the excited modes will be generated just because of the strength of this field and the time of its action. For example, this external field was created experimentally in the group of Vanderlei Bagnato. He called this washing machine. If we apply to the system of a condensed atom with this kind of potential, then with time we see the appearance of different modes. These are typical parameters of the experiment, and the same parameters were used in theoretical calculations. This is what happens if we try applying this field and pump the energy into the system. First, there is nothing, but after 5 milliseconds of pumping, there appear the embryos of vertex rings. which remind some pieces of broken rings, as is here. Pumping longer, and this means that pumping more energy in the system, we see the observation of rings, vertex rings in the system. They appear always by pairs because on the average, the pumping potential doesn't have any anisotropy. It is quite an isotropic pumping potential. Because of this, there is no axis and there is no rotation imposed on the system. Therefore, the vorticities of the rings should compensate each other. And because of this, they appear by pairs. One has plus vorticity, another minus vorticity. Then there appear vertex lines pumping longer. Then vertex lines become deformed, inclined, and after a while, we obtain vertex turbulence. This is the number of vertices that are in the trap due to pumping as a function of pumping time. So first the number of vertices increases, and then here there appears turbulence, it is here, but then vertices become destroyed. And what happens? There appears the droplet state. When the system is composed of both condensed droplets inside the surrounding, which is not both condensed. Some typical parameters are written below. I will not have time to repeat all the details. Then there appears a regime of wave turbulence. Here the picture which describes what is the difference. These are density snapshots. So if we start from the both condensed state and sufficiently long pump of the system, then we obtain this droplet state through the states of ring, vertex, and turbulent state. This is droplet state. These are big droplets of both condensate inside non-condensed surrounding. And this is what happens when we have wave turbulence. There are smaller spots of smaller
Lava, 5 minutes.
Okay. Okay, so this is the difference between the droplet states and wave turbulence, which we can distinguish easily. And we can characterize these quantities by introducing the effective temperature, Fresnel number, and Mach number. And in these characteristics, instead of wavelength of a laser, but which defines the Fresnel number in optics, for example, we take a thermal wavelength. Then we obtain this classification of the created states, starting from equilibrium condensate to wave turbulence through these characteristics. And the final point which I want to show is the creation of an atom laser. You know what is atom laser. When condensed atoms fall out of the trap, and it's possible to see their interference and other coherent effects. But the question is how it is possible to create a directed beam of atoms, not falling, but that could be directed in any direction we would like. For this, it's possible to analyze the behavior of the atomic cloud inside the trap. And it is possible to find such a configuration of magnetic fields and specially prepare the initial conditions when there occurs the regime of semi-confinement of atoms. That atoms are not confined from all sides, they are confined from one side. So all their trajectories either go directly to this direction, or they turn, after moving a little here, they turn and also go in this direction. And that way it is directed beams that can be created. And these are the typical trajectories of this atomic beam as a function of horizontal and attitude directions. And here the trap was directed in 45 degrees to horizon. So we emit atoms in this way, and depending on their initial velocities, they go as typical trajectories. And in this way, we can turn this laser in any other direction if we wish. So I've come actually to the end. What I wanted to show is that between the behavior of coherent modes, there are many similarities with atom optics, many similar effects, which of course are a bit more complicated due to the non-linear equations describing the Bose-condensed system and due to interactions of atoms. Thank you for attention.
Thank you, Slava, for the nice presentation. I see that there are a lot of new topics involving this multimode production of the condensate. So there is time for one question. There is anybody with a question? Well, I have one, Slava. When we produce those excitation of the many-body system, the time evolution is something very, very complicated for the superposition, and this very soon it gets in a kind of turbulent regime because you know, it's hard to keep track of only one superposition and things like this. So in producing this excite type of many-body system, it is expected that very soon the system evolve to a non-equilibrium situation. Is that the case, or I'm just thinking too hard on the problem?
No, this is correct. When we start, for example, from the beginning of the talk, where I was discussing the resonant generation, this pure resonance can be supported, of course, during finite time. Then, because of power broadening, other states become excited and the picture then spreads. We calculated this time, and it's about 1 second. It's possible to up to 10 seconds. So it's possible to keep this more or less pure resonance only during, of course, this finite time, not forever.
Very well, thank you. Any question? Because I cannot see everybody. When you have a question, only raise the hands will not help. You need to open the microphone and ask the question, okay? Okay, well, Slava, thank you very much for the nice presentation and the inauguration of the Seminar 6 of Cold Atoms. Thank you very much. We are now going to call for the second talk, and the second contribution to the seminar will be given by Ivan Castan. Ivan is a long stay in this workshop with very nice presentations, and everybody knows Ivan from the École Normale in Paris. And today he's going to tell us about collective excitation branch in the broken pair continuum of spin 1/2 Fermi gases. So it's another type of application of those quantum fermionic fluids that can be interesting to understand the other physics beyond atomic physics. So Ivan, can you upload your presentation so we can start?
Yes, we are trying to do so, yes.
Oh yeah, now it's okay. It's we can see. And please go on, and I give you a warning 5 minutes before the end, okay?
Thank you very much, Slava, for the Vanderlei, for the nice introduction. So this talk will actually rely on two papers that were published in 2020 in Compte Rendu Physique. So in this talk, I will first present the system, then I will define the problem, I will show how to solve it, and then I will present the results. So our system is a system of fermionic atoms with two internal states, spin up and spin down. We are in 3D, and we are in the non-polarized case. That is, we have some number of spin up and spin down particles. This system is homogeneous in a box. And we assume that there is an attractive interaction between spin up and spin down, short range in the S wave, characterized by a scattering length A. As you know, experimentally, you can tune the scattering length from -infinity to +infinity. So in this talk, we are general, actually. We consider the whole range of possible values of A. The talk is at 0 temperature. And we will use a BCS theory. And according to this theory, the ground state of the system is actually made of bound pairs, spin up and spin down. When the scattering length is negative, as you know, there is no such bound state in free space. So the bound pairs are a consequence of the Cooper mechanism. According to the same theory, those bound pairs form a condensate. And this condensate is characterized by an order parameter delta equal to mean value of psi spin down, psi spin up, and multiplied by some complete constant G0. I will remind briefly two limiting cases. So in the first case, KFA tends to 0-, where KF is a Fermi momentum. This is so-called BCS limit, where the bound pairs are very extended, very large. And then the chemical potential tends to Z1 of the ideal Fermi gas, h bar squared KF squared over 2m. And the order parameter becomes very small, actually exponentially small. As a function of the scattering length. The other interesting limit is the so-called BEC limit, where KFA tends to 0+. Then in this case, there is a dimer in the spin-up, spin-down problem. And the chemical potential tends simply to -1/2 times the binding energy of such a dimer. Actually, the system becomes a condensate of dimers. And then again, in this limit, the order parameter delta tends to 0, but only as a power law to the 3/2. And in between, we have, for example, the unitary limit, where KFA is equal to infinity, which is a maximally interacting regime. So what are the expected excitations of this system? How can you excite this system, right? So the first type of excitation you expect is a collective excitation, where you set into motion the center of mass of the pairs. You don't break them, you simply excite the center of mass of the pairs. And this forms actually an acoustic branch that is with a linear dispersion relation, pulsation omega q proportional to CQ, where the C is the speed of sound. And this is actually a property that you expect in all superfluids with short-range interactions. But in this system, since you have bound pairs, there is a second type of excitation that you expect. This time to be an elementary excitation, where you break a pair. Imagine that in an experiment, you apply an external potential, which would be a cosine Q dot R. This potential can break the pair. The pair initially was at rest, and after excitation, you get a first fragment of the pair, spin up, with a momentum Q over 2 plus K. And a second fragment spin down with a momentum Q over 2 minus K. So the total momentum is fixed by the external potential, it's Q. But the relative momentum K between the two fragments is totally free. It can span R cube. This means that the corresponding energy of the final state, which is the energy epsilon Q over 2 plus K of the first fragment, plus epsilon Q over 2 minus K of the second fragment, this actually spans an interval of R. It spans a continuum going from some lower bound epsilon f of Q to plus infinity. So there is a continuum in the excitation spectrum of the system, even at a fixed total angular momentum. And I call this a broken pair continuum. Here you see I have put actually circles around the spin up and spin down in the fragments, because those are not simply bare spin up and spin down particles in free space, but they still interact with the rest of the system. So they rather correspond to quasi-particles with some dispersion relation epsilon of K. They are so-called the fermionic quasi-particles. And epsilon of k can be calculated with the BCS theory. Basically, there are two cases. In the first case, the chemical potential is positive. You are on the BCS side of the resonance, if you want. Then there is a gap in the system, which is E gap equal to delta, so equal to the order parameter. And the minimum, so the band gap, is reached in k equal k0, different from 0. On the contrary, when the chemical potential is negative, that is, when you are on the BC side of the resonance, so that you still have, of course, a forbidden band gap, which is now given by square root of mu squared plus delta squared, that is, it is strictly larger than the order parameter, and it is now reached in k equals 0. So you have two very different situations. You might believe that maybe that's all. Maybe you don't expect any other type of excitation in the system, but actually, if you are very knowledgeable in field theory, you might know that for this gas of fermions, you can produce an effective low energy Lagrangian on a complex field like that I call now phi, and which is the order parameter out of equilibrium. This Lagrangian has a relativistic invariant form, that is a d mu phi star, and also there is a Mexican hat potential seen by the order parameter, that is a phi star phi minus b phi star phi square. You remember that in the Lagrangian, it's minus the potential which appears. So the potential actually has a maximum when the field phi is 0 and reaches its minimum in some non-zero value of phi. In this case, you know that this is a standard textbook result. You know that there are actually two branches of excitation because there's a U1 symmetry breaking at equilibrium. Phi is at the bottom of the Mexican hat potential somewhere at a non-zero value delta. So you have two collective excitation branches. The first one is the Goldstone branch, which starts linearly with wave vector, omega is equal to q. And this is exactly our acoustic branch, the acoustic branch I was mentioning before. But there is a second branch, which is the X branch, where you actually, the field is excited in modulus. So it can now deviate from the location of the minimum of the Mexican hat potential. And this X branch has a gap. And it has a quadratic start. So omega here in this model would be written as square root of 4b modulus of delta squared plus q squared, where b depends on the microscopic model. It was calculated by Perker, Varma, at least mentioned in this article of 2015, and they predict that little b is equal to 1. That is, this X branch would start at 2 delta. But then we have a problem. We have a problem because we have seen that at least when mu is positive, delta is the binding energy of a pair. So if you predict using an effective low energy model that you have an excitation at an energy 2 delta, you are in a very bad situation because this energy is sufficient actually to break the pairs. So it's out of the validity of the effective low energy theory. So at the end, you don't know if the prediction, this very educated prediction, is correct or not. Maybe it's totally wrong, and there is no such X mode. So this is the fundamental issue we are facing now. So here I've made a plot repeating what I said on the previous transparency. So in the right column, sorry, on the left column, you have the case where the chemical potential is positive, so BCS side. You have the excitation spectrum of the fermionic quasi-particle, epsilon of k. There is a gap equal to delta and a minimum reached in k0 different from 0. And then for the collective excitations, omega q as function of q, you have the Goldstone branch starting linearly, for sure. You have the broken pair continuum, whose bottom actually is flat and equal to 2 delta up to q equal to k0 and starts rising then. And then maybe maybe if you believe in the effective low energy theory, there is a X branch starting at 2 delta, and then this X branch would be in the broken pair continuum. This would be funny. On the right column, we have the case where the chemical potential is negative. So again, this is the BEC side of the resonance. Epsilon K now still has a gap, which is larger than delta. It's square root of mu squared plus delta squared. And the minimum is reached in K equals 0. And in the collective excitation spectrum, what do you have? You still have in omega Q as function of Q, you still have the acoustic branch, which is actually very close to the Bogoliubov branch, because again, this system is mainly now a condensate of dimers. You have the broken pair continuum, which has a parabolic bottom. And then, according to the effective low energy theory, you would have a X branch starting at 2 delta, so below 2 gap. And this would be even more fantastic. That is, you would have an excitation inside the gap. So is that true? Okay, so to answer these fundamental questions, we are going to calculate the excitation spectrum of the system using time-dependent BCS theory. So in short, usually in time-dependent BCF theory, you simply do a variational calculation saying that the state of the system, this is the current state of pair of fermions. But here, we use a slightly different reformulation. We say that the state of the system at time t, this is a coherent pair of fermionic quasi-particles. That is, we take as a vacuum of fermionic quasi-particles the ground state BCS state, psi BCS 0, and we act on it, the exponential of an operator, creating a pair of fermionic quasi-particles, gamma dagger of Q over 2 plus K in spin up, gamma dagger of Q over 2 minus K in spin down, and with unknown, with arbitrary coefficient beta of KQ of T. This is a very convenient reparametrization because if you are in the linear response regime, that is, if the experimentalist applies a very weak perturbation, then those betas will be very small. You agree that beta equal to 0 in the ground state. So if we perform weak excitation, beta is very small. So it's sufficient to do a calculation to first order in beta, which simplifies a lot the calculation. Also, what we find is that the elementary variables, the betas, beta of KQ, it has its own eigenenergy, which is obviously the energy of the pair of fermionic quasi-particles. So it's epsilon Q over 2 plus K plus epsilon Q over 2 minus K. But also it's coupled to the collective variables. That is, the small deviations of the order parameter from equilibrium, delta delta, and the small deviation of the densities and spin up and spin down from equilibrium, delta rho sigma, and all this taken as the Fourier component Q. So after a lengthy calculation, we are able actually to eliminate the betas because delta, delta, delta rho, they depend on the betas. The betas are coupled to delta, delta, delta rho. So we eliminate the betas and we get a closed expression for on the left-hand side, delta theta sub Q, which is the little change in the phase of the order parameter after the excitation, Fourier component Q. Then in the second line, we have the small deviation of the modulus of the order parameter due to the excitation wave vector Q, and then a small deviation of the density from equilibrium due to the excitation wave vector Q. On the right-hand side, what do you have in this vector? S theta, S modulus of delta, S rho. Those are actually source terms which encapsulate the excitation applied by the experimentalist. So for example, if you tell me I perform a Bragg excitation on the system, I can calculate S theta, S delta, and S rho. I plug this in this formula. I apply the inverse of a 3x3 matrix, which is intrinsic, which describes actually the response of the system at complex energy Z to a perturbation. Then I take the Fourier transform and I get the small deviations on phase, modulus of the order parameter and density I need to understand the excited state of the system. So this matrix M has, within this time-independent BCS theory, explicit expressions. Time is running rapidly. So simply, I will not say much more, simply that when you try to apply Cauchy theorem to calculate this integral, usually you want to close the integration domain, the integration contour in the lower half plane. But here, if you do that, you face problem that the matrix M has branch cuts on the real axis, exactly corresponding to the broken pair continuum I was mentioning. So what you have to do then, you have to do analytic continuations to the branch cuts. That is, you have to rotate these branch cuts that are now put vertically as blue lines on this graph. And once you do that, you reveal a pole in the analytic continuation. And this pole will be the Higgs mode we are looking for. So to summarize, in this formalism, you have to solve first determinant of M of Z equals 0 to find the Goldstone mode. Those are the poles on the real axis. You get them for free. But you can also, within the formalism, get the Higgs mode by doing some analytic continuation of the determinant of M and then looking for the zeros. If you don't do analytic continuation, you will never find the Higgs modes. This is what the paper by Ben Fatou 2015 could not find the Higgs modes. Here, this is a little graph again. You see there is a branching point 2 delta. I rotate here the branch cut. This is hatched red line, and under this interval, then I can find by analytic continuation the X branch that varies starting from 2 delta and moving in the complex plane as Q varies. So in short, we confirm that there is indeed a X branch in this system with a quadratic start. So I can give more details. First, when the chemical potential is positive, we find ZQ, which is the complex energy of this X mode, varies indeed as 2 delta plus a proportionality factor multiplied by h plus squared Q squared over 2m. And we have actually calculated this coefficient C. In the BCS limit, you recover the result by Popov. We find that this C has an imaginary part different from 0, which corresponds to the fact that the X mode, being inside the broken pair continuum, will be damped by radiation of broken pairs. In other words, it will be a resonance of non-zero widths, which makes the experimental observation more difficult. So the X mode survives to the existence of the broken pair continuum, but it acquires finite widths. When the delta over mu is getting large above 1.2, that is, you are going towards the unitary limit, strongly interacting regime, then something funny happens that the real part of this coefficient C becomes negative. That is, you have the impression that the mode enters in the gap between 0 and 2 delta. But what happens physically is very important, is that this mode is still separated from the real axis by a branch cut, right? So the experimentalist, like Van der Leyen, is measuring the physics on the real axis above the cut. And our pole is below the cut. So now the fact that the pole is inside the band gap has no real meaning because there is a branch cut between physical reality and this pole, you see? So this means that it will be difficult to observe when the pole is under the branch cut. Okay. When the case where the chemical potential is negative, that is, if here I am in the BEC limit, again, I found X branch. Now ZQ is 2 delta minus BQ squared. That is, the coefficient of Q squared is actually negative, contrarily to what was predicted by the Mexican hat theory. Remember, the Mexican hat theory was predicting X branch was going upward. It was convex. Here we find that it's concave in the BEC limit, but still it starts in 2 delta. So now we have a little bit conflict with Stringari et al., where in their 2012 paper, they say that if you excite a system by changing the scattering length, then you excite Higgs oscillations, and those Higgs oscillations are always at an energy 2E gap. So we disagree with the interpretation in terms of Higgs oscillations. we agree that in what Stringari proposed, there are oscillations at 2 E gap. But if mu is negative, E gap is different from delta. And then those oscillations are not Higgs oscillations, something else. Because the Higgs phenomenon is not due, if you want, to the excitation, to the existence of pairs. It's not due to the breaking of pairs, but it's due to the breaking of U1 symmetry. So the relevant energy scale is not to E gap, but it's to delta, because delta is the order parameter linked to the U1 symmetry breaking. Okay. So to finish, I will propose an experiment where you could see this X branch at least within some range of values of delta over mu. So what I suggest is simply to perform a Bragg excitation of the system. That is, you applied a potential cosine Q dot R minus omega t by applying 2 laser beams on the system. And you excite the system in density. So this is density excitation. Then later on, the experimentalist would measure the perturbation induced on the modulus of the order parameter, modulus of delta. If you do that, then the response function is chi of modulus of delta rho, and I can calculate it as function of omega for a fixed Q with the formalism I was presenting. And here you see the result on this figure. So on the horizontal axis, this is h bar omega minus 2 delta, measured from the gap, actually, here in the case where mu is positive. And on the vertical axis, this is this response function, chi of modulus of the delta rho. It's a complex response function. The real part is plotted in black. You see the real part as a maximum somewhere. Also, it has a singularity here. It's a logarithmic singularity. The imaginary part is plotted in red. You remember the imaginary part of the response functions is linked to the density of states. This is why the red line is actually 0 below 2 delta. So inside the gap, there is nothing. And then when you are above 2 delta, there is a dip. It's rising again. There is another singularity. So now, where is the Higgs branch in this on this figure? Its location, the real part of the Q, is represented by the vertical green line. So you see, by accident, it indicates exactly the position of the minimum in the imaginary part of chi. But in the real part of chi, it doesn't work. That is, the location of the maximum is not right above the Higgs pole. So to do something more serious, what you have to do experimentally is to use the real part, both real part and imaginary part, and do a fitting. I suggest to make a fitting of chi with as a sum of a resonance A over omega minus B. B is the location of the resonance, it's a complex number, and A is the complex amplitude of the resonance. And then you have a slowly varying background, which is C plus omega D. And then if I do that with the theory, it works very well. That is, I'm able to extract with good precision the energy of the complex Higgs mode and also its spectral weight modulus of Z. At least it works when delta over mu is between 0.2 and 2. When delta over mu is getting smaller than 0.2, you are entering the weakly interacting regime, and then it's very difficult actually to see the Higgs mode. If delta over mu is getting larger than 2, then the Higgs mode is passing too much below the branch cut. So since the experimentalist again is only doing physics on the real axis, it can see only the effect of the tail of the Higgs mode, and then it's too difficult to get it with good precision. I think it's time more or less to conclude. Okay, so in the conclusion, we have considered a gas of fermionic atoms at 0 temperature. First, we predict, we confirm, if you want, the existence of a Higgs branch having a quadratic start at 2 delta, where delta is the order parameter and not the gap. This applies both for a positive chemical potential when you are on the BCS side and a negative chemical potential when they are on the BEC side. Second, this branch is always obtained theoretically by doing some analytic continuation on the Anderson RPA equations, but it's not always observable. First caveat, the spectral weight is zero at zero wave number. That is, if you do experimentally an excitation at zero wave number, you cannot excite this X mode. So if, as suggested by Stringari, you modulate, you change the scattering length in a position-independent fashion, you will not excite the X modes, and the oscillations you see are not X oscillations. Second, in some parameter range, this mode is very far from the interval of analytic continuation. So it will be very difficult to see in an experiment, but it would be separated from reality by a branch cut. We still believe that if you do Bragg excitation, this is measurable. This X branch is measurable when delta over mu is between 0.2 and 2. And we believe that Chris Vail actually is a good position to do that because he can do Bragg excitation. And also he has a technique to measure the modulus of the order parameter. Finally, I would like to point out that our study is much richer than this very short talk, because we have studied the wall dependence with the wave number Q, and it's a non-trivial problem. And in particular, we find that in the weak coupling limit, delta over mu tends to 0 plus, there is a rich structure in this X branch involving three scales of energy. Thank you for the attention.
Thank you, Ivan. Thank you for the nice presentation, and thank you for keeping the time of the presentation, which is important for us to move on.
Yeah, okay. I was a bit burning, I have to say, but
yeah, well, it's fine. Oh, we have time for one question, if anybody wants to.
Can I ask a question?
Yes, please, Lucas. Oh, by the way, Lucas Madeira is from Brazil, and he's helped me with the chair of each section, okay? I didn't want to bother anybody, so we're going to be in all the talks, and Lucas is going to help me. Thank you, Lucas, and please go on with your question.
Thank you, Ivan, for the nice presentation. One thing wasn't clear to me. Do you have only contact interactions, or do you put Coulomb at some time?
Okay, so there is no Coulomb interaction in this talk. I assume that the fermions are neutral. But in our paper, actually, we have also treated the case of charged particles. And then if you are in the BCS limit, you still have a X branch. The acoustic branch is pushed up in energy by the Coulomb interaction. You have plasmons. But the X branch still exists and at the quadratic start and starts at 2 delta. So actually, a part of what I said can be applied to supraconductors. But my secret hope is that actually the cold atoms will be the first ones to see this branch, which was actually, to my knowledge, seen in no system at all. So the race is open, let's say. Yeah.
Any more questions? Okay, Ivan, so thank you very much for your participation. It's been always nice to see you speaking and giving always a new aspect of the cold atoms, so it's very nice. Thank you very much.
Thank you, Madani.
Now we're gonna move to the last talk of this first section. And I want to invite Ophir along.
Here.
Okay, Ophir is also a very interesting physicist that's been with the seminar for the very beginning. He is located in Israel, in the University of Haifa. And he always brings nice topics for the theory of cold atoms. And today, Ophir is going to present to us correlation effects in a trapped Bose-Fermi mixture, exact results. So, Ophir, please upload it and go, and I will give a warning if it's necessary 5 minutes before the end.
Do you see my screen?
We see your screen clear. Go ahead.
I try to share to do. Oh, now it's a presentation.
Oh, yeah. Now it's in the presentation mode. Go ahead.
Hello, everyone. Thank you very much, Vanderlei, for the invitation, and I really hope to see you all in person. You mentioned before South America, but also Europe is fine. And I really hope that our session will increase in size, because I remember the times we have been 70, maybe 85 people sitting in a very crowded, only session 6, sitting together. And I really hope we will come back to these numbers. So my talk is actually part of an ongoing project we have here in Haifa, and also in collaboration with my colleague and friend for many years, Len Sederbaum in Heidelberg, which basically follows solvable models of trapped systems. I reported in recent years on bosons, I reported in later years on Bose-Bose mixtures, and actually today I'd like to report on, to be submitted very soon, results on Bose-Fermi mixtures and on correlations that can exist in those systems. Again, all from the point of view of a solvable model. Correlation effects in a trapped Bose-Einstein mixture, exact results. This figure, I hope to come to this figure by the end of my 30 minutes, is an example of correlations between a fermionic impurity and a bosonic bath, depending, of course, on masses and interactions. And the nice features, I hope I'll have the time to develop all of them. If not, you will just enjoy the picture. So what is my setup and the talk's outline? I'm going to present a solvable model for a trapped Bose-Einstein condensate, a Bose-Fermi mixture, and I will begin with presentation of the model and solution of the model, at least the main steps, and then some basic properties. And for me, basic properties are energy of the Bose-Fermi mixture and the wave function, from which in principle you can derive all properties. And then I will settle about one interesting property that I think is quite basic. It's entanglement. We have a mixture of two species, they are interacting one with another, then there should be an entanglement, and we can compute it and analyze it. Then I'll present one detailed application, as detailed as I can in my 30 minutes, which is a fermionic impurity in a bosonic bath. And I'd like to discuss more deeply the correlations that can exist there. And for this, one needs to derive the intraspecies and interspecies reduced density matrices. And once you derive them, you can compute and express the first order and second order correlations, and then discuss their structure. And they will have a structure which is different for the system of non-interacting fermions or bosons or mixture, and we'll make some conclusions, and then a short summary and an outlook. So the models we have been using in recent years to get some analytical results is called the harmonic interaction model. And in the contents of this talk, it will be the Hamiltonian of fermions and bosons. Fermions will be spin polarized throughout my talk. And there is a mixture of fermions and bosons. They are held in harmonic potential, and they are all interacting by harmonic forces. The fermions with themselves with harmonic forces, and a certain strength, the bosons with themselves with harmonic forces, and certain strength, and of course, interaction between them. And it looks simple, but it's actually quite a work to solve the model, and more so from the solution, from the wave function, to extract properties, and on some of them I would like to report to you. So the basic requirement from the wave function, once you solve this model, is to have the right symmetry, the right permutational symmetry, which means that when you replace two coordinates of fermions, and throughout the talk, X is for fermions and Y is for the bosons, when you replace two fermions, the wave function should be antisymmetric, and when you replace the coordinates of two bosons, the wave function should be symmetric. Now, there are techniques that have to be developed, but we don't invent everything from zero. We use and extend techniques that were given in the literature, and the main literature for the techniques are For the bosonic part, is Lee and is Cohen and Lee, B heme, bosonic heme. From Christian Schilling, the fermionic heme, and several papers, including our own, for the Bose-Bose mixture, which some of them are reported in previous years. Okay, so basically, to diagonalize the Hamiltonian, we need to go to normal modes. The normal modes are represented by Jacobi coordinates. And it's useful to work in the Jacobi coordinates of each of the species. So these are the Jacobi coordinates of the fermions. And the last of them is the center of mass of the fermions. And these are the Jacobi coordinates of the bosons. And the last of them is the is the center of mass of the bosons themselves. And then to couple between the center of masses of the fermions and the bosons, and there are two coordinates. One is the relative center of mass of the fermions and the bosons, and the other one is the total center of mass of the entire mixture. Now, this does two things. One, it sets up our normal modes, and in a moment I will discuss the frequencies, and it also indicates the treatment, the separate treatment of the fermions and the bosons, because the fermions, the part of the wave functions due to the fermions has to be antisymmetric, which means we will need to have excitations in the relative coordinates for the fermions, and the bosons has to be symmetric, and at least for the ground state, we do not have excitations in the relative coordinate of the bosons. So once the set of coordinates is defined, we have 4 eigenfrequencies, and they have their multiplicities. So there is the relative center of mass of the Bose-Fermi mixture, and it depends on the number of bosons, the number of fermions, the masses, and the interspecies interaction. The overall center of mass frequency is the trap potential, and there are relative motion of the fermions and relative motions of the bosons, and all depend in a different manner on the masses, on the interaction strength, intraspecies and interspecies. So I like to start with the ground state energy, and the ground state energy basically means that we have occupation of one mode, which is the center of mass, occupation of one mode, which is the relative center of mass, NB boson minus 1 relative populations of the relative frequency, and NF minus 1, which are built one atop of each other. These are fermions, or the relative center of mass of fermions. So this is a closed form expression, and one can study it for many examples, for many limits. One, for instance, can use this expression to benchmark numerical treatments, but this is not the topic of my work. So I pick up one example, which I think is a little bit interesting. I'm taking 1,000 fermions and 1,000 bosons, and the fermions are non-interacting and the bosons are non-interacting, and I only switch on the interaction between the fermions and the bosons. Now, in the absence of all interactions, the energy of the mixture or of the individual particles do not depend on the mass. It depends only on the trap frequency. I mean, it doesn't depend on the mass implicitly. It depends explicitly because the frequency is the force constant divided by mass, but it doesn't depend implicitly. When we have interactions between the fermions and the bosons, then everything starts to be normalized. The energy depends on the mass. And the question is how it depends on the mass. And if it depends on the mass, how it depends on the mass for different masses of fermion and bosons. And this is what we have here in the first plot. And what we see is that if the interspecies interaction is very weak, then there is very weak dependence on the mass. And when we increase more and more the interspecies interaction, then interactions throughout this talk is attractive, is mutual attractives between the particles. Then the energy starts to increase because the bosons and the fermions, they attract each other more and more, and the energy increases. Well, how it increases depends on the mass ratios. Now, if I have a unit mass of the fermions and the bosons, then for a particular interaction strength, the energy increases. Now, if we have larger masses, well, you could say that larger masses are more classical in some sense. Then you need stronger attraction in order to deviate from the non-interacting system. And it also goes in the reverse direction. If you have a very small boson mass, which encircles the fermion mass, then the deviation from the non-interacting system is becoming for much weaker and weaker interaction strength. So this was the ground state energy. A few words on the wave function, which is actually the basis for derivation of all other properties. Now, the wave function, apart from the normalization, has several parts. It has the parts which belongs to the fermions. And this is, if you want to, you can say it's the single particle part and the interacting two fermion part. This is the van der Monte determinant, which necessitates in order for the wave function to be antisymmetric. It's just this antisymmetrized product. And the same you have for the bosons, the one particle part, the two particle part, without the van der Monte determinant. And then there is the interaction part between the fermions and the bosons. And this wave function, analytically given, with some coefficients that are all given in closed forms as a function of all masses and all interactions, allows us to derive all the properties that I will continue to discuss. Let me talk about entanglement between the fermions and bosons, and to discuss the entanglement, I have to go one step before. I have to go one step backward and re-express the wave function of the fermions and the boson of the mixtures in terms of the Jacobi coordinates. And when we re-express the wave function in terms of the Jacobi coordinates of the fermions and of the bosons, it turns out that everything is separable. Everything is separable in terms of the relative coordinates of the fermions and of the bosons. And all the coupling between in the mixture is between the center of mass of the bosons and the center of mass of the fermions and the center of mass of the bosons. And this is the coupling term. Now, taking into account that the metric of the fermion and the metric of the bosons are different, there are different numbers of bosons and fermions and the different masses, if we compensate for this different metric, we can diagonalize these terms using Miller transform. And the final results, I first show you the final results and then I'll discuss it a little bit more. The final results is the Schmidt decomposition of the Bose-Fermi mixtures in terms of fermionic functions times bosonic functions and Schmidt weights. And these are the Schmidt weights, and they are given by explicit form as a function of all masses and the number of particles. And this is the generator of all of the series of Schmidt weights. So now we can ask the question, we have a mixture, there are interactions. What is the entanglement between two ingredients of the mixtures for general number of particles and masses and so on? Here I have the details of the fermionic functions and the bosonic functions and the different scalings, but I think I don't have too much time, then I will jump on that. Let's discuss the entanglement. So this is the entanglement, or the Schmidt generator of the Schmidt decomposition of a system of fermions and bosons, and as a function of actually the interaction strength and for different number of particles. And at least the first conclusions we can make, and these are for 100 and 100, 10,000 and 10,000, million and million, and this are imbalanced. The dotted lines are for imbalanced mixtures. And in order for the entanglement to increase, we need to increase interaction. This is not surprising. In order for entanglement to be maximal for a certain interaction, we need the system to be balanced. This is a kinematical effect because the entanglement is generated solely by the coupling of the center of masses. And there are more surprises here, but in a sense, given a certain mixture for a certain interaction, you switch on the entanglement, and of course you cannot get away with that. And again, you have here a neat model that can allows you to test in other cases where you do not have solvable models. How good are you in calculating, in expressing entanglement in complicated mixtures? Okay, another nice feature here is the reduced dynamics. I will say it in words rather than in formulas. In this model, you have a mixture, fermions and bosons. You have two species. You can precisely integrate out the bosons and talk about, the reduced dynamics of the fermions, and vice versa. You can precisely integrate out the fermions and talk about the reduced dynamic of the bosons. And I would settle for that unless I would like to discuss also collective correlations in the mixture itself, in the combined fermion-bose system. So we need a different approach, not just reducing and integrating out one or the other species. So let me do that for a particular applications. Two fermions interacting in a Bose-Einstein condensate. And here I write the density matrix of the two fermions inside the bosonic majority species. All the normalizations are computed, and analysis, or let's say multiple integrations of this quantity will give us properties. Now, what properties can we ask? I'd like to consider for all the plots I will show you next and the discussion is this, again, the specific case, no interactions between the fermions, no interactions between the bosons. The only interaction is between the fermions and bosons. And we can ask three questions. How the bosonic bath influences the fermionic impurity? Or how the fermionic impurity influences the bosonic bath? And finally, how the two, bosonic bath and fermionic impurity, or fermionic impurity and bosonic bath, are influenced together as one system, because we have a single mixture. I like to start from the second for two reasons. How the fermionic impurity influences the bath. First, because this is the question usually less asked, how the impurity changes or influences the bath. And second, because the bath is bosonic, and looking at correlations and correlation functions at bosonic systems is relatively more simple than in fermionic systems. And I'll start from the second one. How the fermionic impurity influences the bosonic bath. Then I will talk in pictures, I think, from now until the end of my talk. And yes, I have about 8 minutes, I think. From left to right, let's say the interaction or the correlations increases. And let's start from the left column. The left column, we have a situation where this is the first order correlation function, the upper line. The lower line is basically a plot of the reduced one-body density. Two coordinates, we can plot it. It's a geometrical picture of the reduced one-body density, and the diagonal of the reduced one-body density is the density of the system. It's the density of the bath. I have two fermions in the bath, two fermions in the impurity and 1 million bosons in the bath. Now, for weak coupling, I will use this term, or the numbers and the details are here. For weak coupling, we don't see the correlations in the bath. But we need a measure. We need a measure to compare the size of the bath and the length scale of the correlations. And the measure is the comparison of the scale on the plot where changes happen. So the length scale here, where changes happen, that is much larger than the size of the plot, is much larger than the size of the bath. No correlations in the bath. We make the coupling between the impurity and the bath stronger. When we make the coupling between the impurity and the bath stronger, and remember, our tools to do that are the interaction between the impurity and the bath, and the relative masses. You don't have other. When we make the coupling stronger, we start to see correlations embedded onto the bath by the impurity. And we see a decay from high, 1, this first order correlation function, to low, here not yet 0. So at least visually, we can see a length scale of the decay. We couldn't see here. We could see a length scale of the decay of the correlations, and it is, I would say, of the same order of the size of the bath. And look, the bath here, it looks circular, and here it looks circular. Still, the correlations inside the bath are not strong. In a moment, we'll see the function, then circular will be circular. When we go to strong coupling between the two impurities, and the bath, we see faster decay of the correlations in the bath. And in this case, the length scale of the decay is smaller than the size of the bath. Actually, the bath size is larger because it's more attracted to the fermions. Then we have correlations imprinted onto the bath by the fermionic impurity of much larger length scale than the bath, of comparable length to the bath, or of smaller length to the bath. So this is the bosonic bath. And again, bosonic correlation functions are simpler than, I'll give the formulas here, something that will be more difficult to do for the other example. So this is the analytical reduced one-body density of the bosons of the bath. All the fermions are integrated out, and this is the density. And as long as this coupling, again, it's analytically computed, is very small, the bath looks circular. Once this coupling increases, we see a distortion of the bath. And this is the standard definition of the first order correlation function. And as long as this is 0, it's non-interacting, it would be flat. And once it increases, then we see the decay of the bath. Going back, small coupling, intermediate coupling, large coupling. And basically the plots are these functions, nothing else. We can equally do the same for the second order correlation function. Second correlation function is not limited by 1, so it enhances, it's a magnifying glass for correlations even more. Then these are the 3 plots panels we had before. Weak coupling between the impurity in the bath, intermediate coupling, a strong coupling. And again, we see the length scale, much larger than the bath, of comparable size to the bath, and shorter than the bath. And there are decay of correlations on the off diagonal and increase of correlations on the diagonal. This has to do with the type of interaction, and many other things can be done and can be computed. But the one point I'd like you to pay attention, again, it's kind of unexpected. These are intraspecies correlations. They are symmetric to the exchange of the 2 coordinates. It cannot be other way in an interspecies analysis. Let me talk now on the impurity, to the first question. What are the correlations imprinted by the bath onto the impurity? Now, fermions are more difficult to analyze than I needed another more row. These are the non-interacting, 2 fermions, non-interacting. This is the first order correlation function, and this is the reduced one-body density, and the diagonalized is the density. So 2 fermions, there is the node between them, and basically there are maximal correlations on the diagonal and maximal anti-correlations on the off-diagonal due to the Fermi statistics. Now, in the other 3 panels, we make a coupling. We make an interaction between the fermionic impurity and the bath. And again, weak coupling, intermediate coupling, and strong coupling. So what's the difference? And what's going on? When we have weak coupling, you could say that nothing happens. But actually the scale here, because the plots look nearly the same, both the reduced one-body density and both the correlation functions and the reduced one-body density. But the major difference is the scale. The scale here is 10 times smaller. Weak coupling, weak attraction between the impurity and the bath. The impurity becomes smaller because of the attractive forces with the bath. But otherwise, there are weak correlations, and we need the comparison to the non-interacting fermions, to the structure, to make sure of that. For bosons, it's flat, so it's easier to make. Now let's talk about intermediate correlations. What's happened in intermediate correlations? At intermediate correlations, we have the fermionic nature of strong correlations and strong anticorrelations, but now there are decay along the off-diagonal, this exponential decay along the off-diagonals. If you look at the reduced one-body density pictorially, you don't see much differences. But the decay of correlations here is already at the size, at the length scale of the size of the fermionic impurity itself. When we increase the coupling between the impurity and the bath, something severe happens to the fermionic impurity. It's being stretched. The density, these are all the same scales. It's being stretched. It's being stretched. You see the fermionic nature by the nodes, by the positive and negative, but you could hardly see the minimum that you have in a fermionic wave function, the node. Everything is stretched, and in terms of the length scale of the decay of the correlations here is much shorter than the size of the fermionic impurity. And we can equally, these are closed form expressions, and one can understand from them what's going on, but it's more complicated naturally than for bosons. We can equally look at the correlations and the two-body correlations, and we are getting pictorial here. Again, this is the structure of the two-body correlations. Weak coupling, just scaling the attractive. The system is becoming 10 times smaller. But when we make intermediate correlations and strong correlations, everything is distorted, and we are getting a highly correlated pair, two fermions, due to the strong attraction with the cloud. I guess I need to finish soon. Then I want to go.
You have 3 minutes.
3 minutes, I will finish. It's okay. This is actually the picture I was aiming, because these sort of studies, the ones that requires going beyond the dynamics of only bosons or only fermions. I mean, this is the second order interspecies correlation function, combining the fermion and bosons as a single quantum entity. This is the non-interacting. The non-interacting, you see here the fermionic nature, and there are no correlations. Everything is flat. Everything is flat because the system is separable. It's fermions times bosons. Now we start to switch on the attraction, the interaction between the fermion and the bosons, and we start to have buildup of correlations. And in this length scale is comparable to the size of, this is a distinguishable pair, a fermion-boson amalgam. And this length scale of the decay of correlation is shorter than the size of this boson-fermion amalgam. And if we do not pay close attention and we think, hey, this is symmetric because the coupling between the bosons and the fermion has a certain shape, bosons and fermions in our mixture, or always, they are distinguishable. So concerning correlations, we have another degree of describing the correlation, the polarity, how the correlation function is rotated, because you cannot interchange a fermionic coordinate and a bosonic coordinate And you can really get some weird things about these amalgams of bosons and fermion in the strongly correlated Bose-Fermi mixture. Summary and outlook. We have presented a soluble many-body model for a trap Bose-Fermi mixture. We have discussed basic properties, energy, wave function, and we have discussed briefly basic properties, energy, wave function, entanglement as a function of all parameters, the number of bosons and fermions, their masses, and the interspecies and interspecies interactions. As an application, we discussed briefly the correlations in a fermionic impurity induced by a bath, in a bosonic bath induced by the impurity, and interspecies correlations mediated solely by fermion-bosons interactions. We briefly discussed length scales and other properties, polarity of correlation functions. What next? I don't know, many things, excited states, everything was for the ground state, dynamics, highly challenging, angular momentum, exchange of angular momentum between species and more species. Thank you very much.
Thank you. Very nice presentation. So we have time for a question. Maybe I can start off.
Yes.
My question is in the last possibility you put, which is the exchange of angular momentum between species. How that, because we know that if I have a species, I have a mixture, and I put angular momentum in one, that will oscillate between the two species, right? Because of the coupling. So this is what you envision to do or to analyze, or is something else?
Okay, then here I have to say that we have an example for Bose-Bose mixture of angular momentum and how it's distributed between them. And well, it depends on the coupling, because the coupling between them changes the excitation spectra. So you could have resonance states and other states that are special in this system. Now, for bosons, I think I understand what's going on, because both of them are, let's say, Gaussian-like. But for fermions, there are more kinds of excitations, and I don't know what will happen.
Do you think that by having a mixture, we can like suck the angular momentum from one species? So I can produce turbulence, hydrodynamic turbulence in one species, and suddenly remove all the angular momentum and have it clean again. So we have a knob to control this phenomenon of turbulence in a quantum system.
Okay, I can only say what we found for this model for bosons.
Oh, I want to know what you feel.
Okay, in these models, there are zero modes. Zero modes allows you to suck completely all the angular momentum from one species to another. I guess that in the lab, you would have maybe a width to that. You would have a resonance that you, for certain parameters, able to suck most of the angular momentum from one to another.
Okay, well, that's controlling turbulence. That's an interesting concept. Okay, if there is no further question, I want to thank you all for being in this section. I want to remind you that we have a break, a coffee break. Each of you will have a coffee in a different place with a different flavor, but it is a coffee break. And then we have the plenary section and the official opening of the workshop. And then we'll be returning at 4 p.m. UTC time. So you have to calculate what is your local time to be back. Mm-hmm. And we're going to start with Alice, that's together with Ivan. And then we have, so she's going to give the first talk of the afternoon section. And then after Alice Sinatra, we're going to have Salansnik, also with a group from Italy, speaking about Berezinski, Coulter-List, Taulis type of phase transition. And finally, we ended with Andrea from Spain, speaking about ghost vortices and how to turn them real. it's nice to see how we can turn a ghost in real objects. That would be nice. Okay, so I hope you all come. We had a wonderful start, so let's keep going that way. Thank you very much, and see you at 4 p.m. UTC time. Thank you for all. Bye-bye.
See you later.
Bye.
Oh, it's the same link, okay? Use the same link for all the seminars. Okay. Thank you. Bye-bye.